So let me introduce you to something called a GPU, because lots of deep learning code is actually in reality is executed on a GPU and not a CPU. We all know what a CPU is, right? CPU is literally the computational unit that we all use in any modern computer, right? Let me explain you what a GPU is and how it is different from a CPU and why we need GPUs for deep learning, right? So GPU stands for graphics. GPU stands for graphics processing unit. And CPU, as most of you know, stands for central processing unit. The word graphics here tells you a lot about what GPU does. GPUs became very, very popular in late 90s and early 2000s. In late 1990s, they actually came into the scene actually in late 1990s, early 2000s, and they are mostly used even today. GPUs are extensively used for gaming, right? If you play any high-end game on your laptop or desktop, you would need a GPU, so that because GPU can process, gaming is very, very computational intensive. Just imagine you have to render lots and lots of uh, dynamic video on your screens. So gaming requires a lot of computational power. Gaming requires lot of computational power. Lot of computational power. By gaming, I mean like realistic 3D gaming, not some simplistic 2D games, right? Realistic 3D gaming requires lots of computational power. And that additional computational power actually comes from GPUs. Okay, even though GPUs were initially built for gaming consoles, they became extremely popular tool in deep learning. I'll show you why. I'll argue why it is so. First, let's understand the architecture, a high level architecture, not a very detailed architecture of a CPU and a GPU. Right? Let's understand the difference between both of them. In a CPU, you have your RAM here, right? RAM basically is all of your memory, right? 64 GB of RAM, 4 GB of RAM, etc. This is not your hard disk. This is your random access memory. This is your RAM. Now your CPU is here, right? Your RAM has all the data, right? Your CPU is here. Within your CPU, you typically tend to have multiple cores in modern CPUs. Let's say you might have 4 cores: core 1, core 2, core 3, and core 4. Okay, this is my core 1, core 2, core 3, and core 4. So in a multi-core CPU, so each of these is a core. In a multi-core CPU, you can have 4 computational units that can run in parallel. Okay, so maybe your songs are being played by this core, okay, while your internet browsing is enabled by a different core. While if you're watching a movie or watching something on YouTube, probably that's being rendered using another core, etc. So these cores can work in parallel, and this space in between is called cache. This space, this area is called cache. And what is cache literally? Cache is basically, and this all is on a single chip. Remember, this whole thing is on a single chip. Okay, the RAM and CPU are connected through motherboard. Okay, your RAM and CPU are not on the same chip. Okay, your RAM is outside the chip. Okay, so cache is like in on chip memory, is basically on chip memory. Okay, typically much smaller than your RAM. Okay, so what it does is, the closer you are to each of your cores, the faster you can access that. So cache is literally a space where, suppose if I have, let's say, suppose if I'm trying to do this, if I'm trying to do this operation, let's say I have a matrix A and I'm trying to multiply it with a vector B. This is matrix A and this is vector B. Okay, simply speaking, this is matrix A and this is vector B. Let me erase this to show what is happening, right? So this let's say this row is A1. Okay, this row is A2. This row is A3, so on and so forth. And this whole thing, let's call it just B. So to multiply both of them and get a result, what do I have to get? First, I multiply this row with this column. So I have A1B. So let's say A multiplied B is C. The second entity is A2B. Third one is A3B. So on and so forth. Okay. So what happens is, because B is being used to in this computation every time. So let's say zoom. So what do I need? So I'm multiplying A1 with B, A2 with B, A3 with B, etc. Which means B is being used in every multiplication that I have here. Because it's being reused so many times, it makes sense to store B in the cache. So I'll store B in the cache. And some parts of A also I'll store it in the cache. Because since the cache is on the same chip, cache is also memory, literally. Cache is also memory. Since this memory is on the same chip as the CPU, the processors or the cores can access this much, much faster than the RAM. Right? So whatever you're reusing more and more and more, you typically tend to store it in cache. Okay, this is how it works. This is your simple CPU. And a simple CPU can process 4 parallel tasks, which means while you're one thread, okay, it could, if you write your code carefully using multi-threading, etc. Okay, on this core you might be running A1 multiplied by B. On this core you could be running A2 multiplied by B. On this core you could be multiplying A3 multiplied by B, A4 multiplied by B. And once these multiplications are done, you can multiply A5 with B here, A6 with B here, A7 with B, A8 with B. You can do it parallelly, right? And your B is stored here. Your A, parts of A are stored here. Okay, whenever a new part, let's say A5.B is not available in the cache, it will bring it from RAM. Okay, this is how your CPU, this is like a very, very high level overview. There are lots of intricate details for which I'll have to teach you all of computer organization and microprocessors, which is like a whole 2 semester, 3 semester subjects, okay, in computer science. But I'm giving a very high level overview here. What a GPU does is very different. Okay, let's go to a GPU. This is how a CPU operates. Okay, anyway, since we've used this page, let me finish CPUs here. Okay, so what's happening is at any one instance of time, A1B, A2B, A3B, and A4B are being run parallelly. Okay, this is they all 4 can run parallelly because I have 4 cores, and if I program carefully using multi-threading, I can do it. Then A5.B, A6.B, A7.B, A8.B can be run in the second timestamp. So first probably it takes 1 millisecond to run this. Once these are done, in the second millisecond I run this. In the third millisecond I run it again, so on and so forth. But at any time, parallelly I'm running 4 tasks. So 4 parallel tasks. And CPUs are designed for general purpose programming. CPUs are, you can play music here, or you can do mathematics, or you can play a video. It's very general purpose. Okay, you can use Microsoft Word or Excel. It's a very, very general purpose computation units. And CPUs are very, very fast. Typically you see things like 2 gigahertz, right? So 2 gigahertz basically says how fast this CPU can operate, how fast it can compute, right? You typically have 2 to 4 gigahertz processors today, right? So now let's go to a GPU. A GPU has a very, very different architecture. Let me explain this. You have your RAM. Sorry, let me draw it properly. So you have your RAM, just like in the case of your CPU. But the structure here is very, very different. The computational structure. This is your memory unit, right? See, this is your memory unit and this is your computational structure. This is a single chip, right? So on a single chip or a small set of chips within the GPU, what you see is this. Instead of one processor, you see lots of processors. Or instead of 4 processors, you end up seeing, okay, so each of these, so let me draw it first. So each of these is a processor. In a typical processor today, you see 4 cores or 8 cores or 6 cores, typically. Okay, there are also single core boxes, etc. In a GPU, it's very common to see hundreds of cores, even thousands of cores, sorry. So there are GPUs where you can get 1024 cores or even 2048 cores. So each of these is a core. So you have lots of small processors, but each GPU core is much slower is much slower than a CPU core. See, your CPU cores typically are operating at a 2 gigahertz frequency, or you can think of this as speed, right? While a GPU typically operates at a few hundred megahertz, maybe 400 megahertz, not even at a gigahertz speed. Okay, your CPUs typically operate at 2 gigahertz, and a gigahertz is 1000 megahertz, or to be precise, 1024 megahertz. Okay, so your GPU cores are much slower, but there are many of them. And in each core, so let me take this one block here. Okay, this one block here. Okay, I'm just expanding on the single block. This single block has two things. It has a processor, it has one core, it has a cache. It has two things. So the structure internally looks like one core and one cache. Here, if you notice, your one cache that all the processors are sharing. On the other hand, what you have here is you have this cache. This is called distributed storage, distributed cache. So literally what you have in each of these units is you have a core and a cache. Okay, I'll show cache with dashed lines here. So if you look at this, you have a processing unit here and you have a memory cache here. Similarly, if you take any of them, any cell, you have processor unit here and you have cache here. So what you have here is distributed cache. Is a distributed cache. And the memory, the sum of all the cache, okay, the sum of all of the distributed cache is called video RAM. Okay, so you might hear with GPUs, people may say, okay, this GPU has 2048 cores and it has a VRAM of 8 GB. What they mean when they say VRAM of 8 GB is basically, if you sum up the storage that is there in all of these caches across these thousands of cores, the sum of all of them is 8 GB. And since this data and this memory or this data is very close to the computational unit, it can perform an operation on this data very fast. This core can operate on this data very fast. And the way it operates is, whatever data GPU wants to operate on, it will first get it from RAM. It will first get the data from RAM, distribute the data across all of the cores in the best or optimal way, and you can mention it in the code how to distribute this data. Okay, if you write low-level GPU code, okay, there's something called as CUDA. CUDA is a programming environment or a toolbox, you can think of it, to actually program NVIDIA GPUs. And by the way, NVIDIA is one of the largest makers of GPU cards in the world today. Okay, and CUDA is a programming interface through which you can say, okay, this is the data that I have in my RAM. Which part of the data should I bring it to each of these cores? How should I build my distributed cache? So the way it works is some data which is there in the RAM through CUDA, and of course your TensorFlow, Keras, all of them use CUDA internally. Okay, so but what's happening here is, if I have some data in the RAM, I can define how this data should be split across the distributed cache, and any operation that I give can now run. This core can run an operation here, this core can run here, etc. So GPUs, since they have thousands of cores as compared to a modern processor which has only 4 cores, it can do a lot of parallel operations. Okay, so in a GPU, our A dot B will work like this. You have A1B, A2B, A3B, A4B, all of it A1000 into B, all happening simultaneously. Now A1001B, A1002B, A1003B, so on and so forth, A2000B happen in the second time step. Okay, so here you have 4 parallel tasks. Once the 4 parallel tasks are over, next 4 parallel tasks will start. In the case of GPU, 1000 parallel tasks, literally 1000 parallel tasks are running at one instance. Once these are over, then we are starting with the next set of parallel tasks. And to do all of it, remember, everything is being multiplied by B. So what I do in my distributed cache, suppose this is my GPU, okay? Let's assume this is my GPU. Okay, and I have cache here, right? So what I'll do here is, First time, in this first iteration, I have thousand of these. In the first iteration, what I'll do here is in this memory, in this computational unit, I'll store A1 and B. In the second one, I'll store A2 and B. In the third one, I'll store A3 and B. In the fourth one, I'll store A4 and B. The fifth one, I'll store A5 and B. Because if A1 and B are available here, this core can perform this multiplication very, very fast. So I'm distributing my A and B carefully so as to enable this A dot B, the matrix A dot vector B operation very, very efficiently. And this is very possible because I have lots of cores and I have a smart way to distribute my data. Here I have A6 and B. Okay, in the cache, I'll put A6 and B. This computation unit will compute A6 and B. Remember, even your A1.B is basically an operation like this. This is your A1, right? And this is your B. Even this operation requires some multiplications and additions, isn't it? That will be performed by this core. And because I have thousands and thousands of cores, GPUs tend to be much, much faster if you have parallelizable tasks. So this is the core thing. GPUs are fast. GPUs are fast if you have parallelizable tasks. Parallelizable tasks. Okay. Remember, multiplying a matrix with a vector is highly parallelizable because my A1 multiplied by B doesn't depend on A2 multiplied by B, which doesn't depend on A3 multiplied by B. All these can be performed by different computational units, isn't it? Because matrix operations. Remember, what is all of deep learning if you think about it? Deep learning literally has a lot of matrix multiplications and additions. It's all basically a bunch of matrix or vector. You can think of it as matrix multiplication or vector multiplication and additions. Or you can think of it broadly as tensor operations. You can think of them as tensor operations. Okay, you're basically doing a bunch of matrix or vector multiplications and additions. That's what it is. Look at an update, right? You have W at time t is W at t minus 1 minus eta times the derivative with respect to W. Now, instead of 1W, if I write this as a vector of W's, right? If my capital W is a vector of all the weights that I have, okay, I can write my capital W at time t as capital W at time t minus 1 minus eta times the derivative of L with respect to my vector. So this is vector operations. See, this is a vector, this is a vector, this is a vector. So instead of doing operations on single weights, I can perform operations on the whole vector of weights or matrix of weights, isn't it? And what is this? This is basically a vector. This is basically a vector, and you're doing a difference operation, or you can think of it as an addition with a minus sign, right? So lot of deep learning stuff is literally matrix multiplication and matrix additions, or to be precise, it's basically tensor operations, basic operations like multiplications and additions on tensors. And these tensor operations, these tensor addition and multiplication are highly parallelizable. You have seen an example, right? This A1.B can be done in parallel to A2.B, can be done in parallel to A3.B. Similarly, adding two matrices. Adding two matrices can also be done parallelly because this addition plus this addition has got nothing to do with this addition plus this addition. If you're adding two matrices, right? It's because lot of the tasks that we have in deep learning are highly parallelizable tasks. And since GPUs have thousands of cores and very, very efficient distributed cache, right? GPUs tend to run, in reality, when you actually run deep learning algorithms on GPUs, they tend to be 10 to 100 times faster, 100x faster. They tend to be really, really, really fast. Okay, and those of you who may wonder, okay, which means do I really need to buy a GPU now to do deep learning? If you have the monetary resource, if you have the financial resources, these are some of the most popular GPUs. There is something called GTX 1080 Ti, GTX 1080. All these are NVIDIA. All these are NVIDIA GPUs. 1070, 1060, 1050. Of course, I think this has 11 GB of VRAM, if I'm not wrong. This has 8 GB of VRAM. right? The more VRAM you have, the more parameters you can have in your deep learning model, right? So in a nutshell, if you have more VRAM basically implies you can build more complex models, with more weights, because all of your weights are what you will store in the visual RAM, or it's also called as video RAM. Video RAM is nothing but your distributed cache. Video RAM is nothing but the sum of all the distributed cache that you have in your GPU. So the more the RAM you have, more complex models with more weights can be trained. Right? The more VRAM you have. So these are some of the most popular models, and they're not cheap, trust me. On Amazon.com, a high-end GTX 1080 Ti, it has 11 GB of video RAM, costs about $1,000. In India, if you go to Amazon.in, it costs about anywhere from 79,000 rupees to 1 lakh rupees. Okay, so it's not cheap, but if you have the financial resources, it's a good investment for you to buy. If you're planning to do deep learning for the next 3 to 4 years, it's fully worth it. For those of you for whom the financial resources are tight, or those of you who think, I don't want to buy this right away, I want to first experiment with it. In the next video, we'll show you an online tool called Google Colaboratory. It's also called as Google Colab for short, which is an online tool that is provided by Google Research for education and research purposes, where you can run your high-end, your complex deep learning models on Google's cloud. On Google's cloud you can run, which has both GPUs and CPUs. Right? We'll show you how to use Google Colab in the next video. But if you have the financial resources, please go ahead and buy it. But don't buy it right away. I would say play around with deep learning for a while on stuff like Google Colab. By the way, you can also do deep learning on CPUs. Don't think you can't do deep learning on CPUs. You can do deep learning on CPUs. It will just take more time. You need more patience. That's it. Okay, when I first learned deep learning, I actually used my MacBook Pro and I learned it on that. Eventually, of course, we got our own high-end GPUs, clusters of GPUs, and things went very well from there on. But we'll show you Google Colab, which is a very, very nice online tool for you to practice. Even if you have a very, very low-end computer, we can use Google Colab, which is an online tool, so that you can learn some of the deep learning. And don't buy it right away. Play with it for a while. Only when you're convinced. My recommendation to anybody who's planning to buy this is this. If you have the financial resources, my recommendation is this. Only buy these if you're sure that you're going to do deep learning for the next 2 to 3 years. If you're very, very serious about training hundreds of models over the next 2 to 3 years, only then spending maybe a lakh on each of these, or maybe $1,000 on each of these is worth it. Otherwise, please don't buy them and waste your money.